So I'm just going to give a recap of everything, TK. So we have in redox reactions, you've got reduction happening, which is a gain of electrons. When that happens, the charge decreases, oxidation state decreases. Like if you have positive charge, it becomes less positive, it decreases. And if you have oxidation happening, which is a loss of electron, the oxidation state goes up, it increases. And the thing becomes more positive when it loses electrons. If it's -2, it becomes 0, it increases. -3 becomes... So the oxidation state would be increasing when oxidation is happening. And we did redox reactions, the same thing that you did in AS as well. So we talked about balancing redox equations. I told you about that in redox equation, it's the atoms should be balanced, but the number of electrons that are gained and lost, they must be made equal as well. Like for over here, you have Na going to +1, so that means it lost 1 electron. Al3 plus goes to Al, so that means it gained 3 electrons. So the number of electrons gained and lost must be equal, so which is why you should have 3 sodiums, because then the number of electrons lost by each of the Na would become equal to the number of electrons gained by one of the aluminiums. So the electrons gained and lost, they have to be made equal. So we did all of that. And in the last class, we started with the main concept of electrochemistry, which was that we started talking about electrode potentials. So I'll just briefly redo that because that's very important. Uh, what we're going to learn in the chapter is we're going to learn what would happen if two things react. Like over here, if I have Fe3 plus and I have copper 1 plus and I want them to react, then how would I know who's going to gain electrons and who's going to lose electrons? Because there's no way to figure out who's gaining electrons, who's losing electrons. If I tell you that there is aluminium trying to react with, let's say, lead or some other element that you have never heard of, uh, then how would you know that who's going to lose electrons, who's going to gain electrons? So we need to somehow figure out the tendency of which element or substance or compound is or wants to lose electrons and which ones want to gain electrons. So I gave you this idea of what electrodes are. So for example, so I'm going to do a sodium one first, and we're going to discuss a few more electrodes. So it's just going to be a recap initially of what we did yesterday. So if I want to know, let's say I want to know that what does sodium like to do? Now, sodium is one element that we are very sure of what it wants to do. It's a very reactive element, and it always wants to, it's a very reactive group 1 metal, and it always likes to lose electrons. We're sure of that. So which is why I'm picking that. But how do I give it a value? Like, what is the exact tendency of it losing electrons? How would I figure that out? So what you're going to do is you're going to take a piece of sodium and you're going to place it in the beaker. So here's your big chunk of sodium, and you're going to place it in a solution that contains sodium ions in aqueous state. So the solution contains sodium ions in aqueous state. Now we exactly know that what would sodium do? Sodium would immediately start losing electrons, and immediately it will start to turn into turning into sodium ions. So there's going to be more and more sodium ions that are going to be produced in the reaction. So a lot of sodium ions are going to be created because sodium really likes to lose electrons. So lots and lots of sodium ions are being produced.
Sir, but how is sodium metal reacting to form sodium ion?
Sodium likes to lose electrons, right? So, I mean, it has a very strong tendency to lose electrons. Where would all the electrons go? The electrons would start accumulating on the metallic rod. Because what does a metallic rod look like? I mean, there would be more and more electrons being left behind. Because a metallic element, I mean, that's the giant metallic lattice, which looks like this. Just a second. So I'll just copy paste this over there. So the metallic rod can accommodate a lot of electrons. That's why they conduct electricity. So this is so more and more electrons would be left on the metallic rod because sodium would be constantly losing electrons, and there's going to be a buildup of negative charge on the metallic rod. Uh, the negative charge would become larger and larger, and eventually it's going to become so large that the reverse reaction would kick in. That instead of sodium losing electrons, the negative charge, this very large negative charge, which is building up on the metallic rod, over here. So this very large negative charge, there would be more and more electrons. So this process would not happen indefinitely. It will stop at a certain point. At a certain point, there would be so much negative charge that's built up on the rod that the sodium ions would be attracted back to it. And
Still, again, I don't get the fact that sodium is a metal and it will only react when it is in contact with a certain type of element. So, यहाँ पे तो it's only in contact with other sodium ions and
nahi,
water.
on its own, listen, on its own, uh, even on its own, it will try to gain electrons. Lose electrons because the metallic rod can accommodate electrons. Do you get the point?
G, yeah.
Sodium is basically trying to give electrons to the metallic rod that's behind, because the metallic rod, I mean, there are lots of spaces in it and it can accommodate electrons. Like if you had a non-metal, then the non-metal would be gaining electrons, right?
G.
Acha,
And this metallic rod is made of sodium, right?
yes. So over here, so the thing is, sodium will not lose electrons indefinitely. Okay? It's going to stop at a certain point. Do you get the point why it's stopping? Because of that, because you need someone to gain electrons, and there is no one gaining those electrons. Do you get my point? Like sodium initially would try to lose electrons. I mean, because sodium, and why would sodium try to lose electrons? Because the outermost electron of sodium is really far away. So it's not really attracting that outer electron that much. So that electron, there's a very bright chance of that electron getting lost on its own. Even if there is no non-metal trying to gain that electron, sodium would still be losing this electron, but it would only do that to a certain extent, to a very minor extent. Is this clear? Ibrar, is this clear?
Yes, sir.
Achha, which is why the whole sodium rod is not going to react, because there is no one gaining the electron. So immediately once the first few sodium ions are formed and the electrons are left behind, the electrons have no place to go. I mean, there's no one gaining those electrons, right? So there's going to be a lot of negative charge that's building up on this rod. And immediately what that negative charge would do is that it would start to attract the sodium ions back again, and that would result in this reversible reaction where sodium would actually stop losing electrons, because sodium would try to lose electrons and form sodium ions, but at the same time the sodium ions will be attracted to those electrons back again. So there's a back and forth reaction that would be happening where forward and backward both would be going on. Is this clear to everyone? Ethan, is this clear?
Yes, sir.
Achha, so
Sir, if I have the sodium rod, just the sodium rod without the water, what is the water basically doing? Would the same thing still happen, that the sodium would still lose electrons?
nee, but the ions would not be able to dissolve. It's because the sodium ions, I mean, it's the metallic lattice. If you just have a sodium rod, the electrons would be lost, right? But the ions would not leave.
Exactly.
So the net charge on the
So,
sodium rod would remain zero.
but the electrons would still leave even at that time.
even in that time it would leave, but the net charge on the
Okay.
rod would remain constant because the sodium ions are dissolving and leaving. So that results in this large negative charge that builds up on the rod.
I get it.
Now the main point is, because sodium really likes to lose electrons, there's a negative charge that's built up on the rod, and we discussed yesterday. What you just have to do is take a voltmeter and you measure the voltage of the rod. Just 1 second, my board is hanging up. So what you just have to do is connect a wire connected to a voltmeter, measure the potential on the measure the potential on this rod, and that's going to be your E naught. And once this equilibrium is established, the negative charge that's built up remains constant, because every time electrons are lost, there would be some sodium ion that would be gaining those electrons back again. So the net charge would become constant. So that's known as your electrode potential. And that value, if it's negative, it's very negative. That means the element or the substance or the metal, whatever it is, it really likes to lose electrons. So this is what we did yesterday. We talked about this, and we talked about standard electrode potentials. That it's the potential difference that's calculated on these electrodes.
So
Is
does
this
voltmeter give readings in negative forms? Matlab, does it give
yes?
reading in minus? Yeah, it does.
I mean, yes, it does, because volt. So remember voltage. I'll come to voltage again. Voltage is potential difference. Uh, so it's basically higher potential minus lower potential, right? So it depends. Which one are you taking? Because it's a relative value, right? So it depends which one are you taking as the higher potential. Do you get my point? And which one is
Yes.
being taken as the lower potential? So negative just means that it's a lower potential. And remember, I told you slightly that when you talk about voltages, the negative and positive in reality, they don't really make any sense. It's potential difference. It's always higher potential or lower potential. So negative just indicates that it has a lower potential. It's got more electrons. There's more negative charge on it. But voltage is always a relative term. But I'll discuss that later on. Okay, let's just discuss electrodes first. I said now I'm going to discuss an electrode where a positive potential would build up. So what kind of electrode would that be? Let's take an unreactive metal. For example, I've got copper. Now the thing with copper is that copper doesn't. It's very unreactive. It doesn't really like to lose electrons. It doesn't really like to form. It doesn't really like to form positive ions, right? So it doesn't like to do this. It likes to do the opposite. Like the ion likes to actually gain electrons. So it wants to do the opposite thing, but not the. It wants to gain electrons. Like if there's a copper ion, it would quickly try to gain electrons. Uh, because copper and transition metals are unreactive, and the main reason why they're unreactive is because they have a lot of protons. So it's very hard for them to actually lose electrons. So if they have lost electrons and they've formed ions, they would quickly try to gain those electrons back. So the forward reaction would not be happening that much. So let's make an electrode out of copper. So I'm going to take a copper bar and I'm going to put it in a solution that contains copper 2 plus ions. So this is my. Let me. Okay, so this is my copper rod, and I have got copper 2 plus ions in the solution. Now remember, the metallic rod. The metallic rod has these delocalized electrons in it, right? So, so you have this metallic rod. It's got these delocalized electrons, and these copper 2 plus ions, they would really like to gain those electrons. So they would start to like gain electrons. So the first reaction that would happen is initially, as soon as you drop this copper in copper 2 plus ions, the copper 2 plus would, because they're very unreactive, they like to gain electrons. They have a tendency to gain electrons. They would try to gain electrons and form copper. So you would immediately start seeing a deposit of copper forming on this metallic rod. So the copper 2 plus ions would be constantly gaining those electrons from the metallic rod, and the metallic rod would become electron deficient. There's going to be, because the copper ions are taking all the electrons away from it. So there's going to be more and more positive charge building up on the metallic rod as this process continues. As more and more copper ions come in and they try to gain those electrons. Is this clear? This part. Minahil, is this clear? Rubab, is this clear? Zahib?
Yes, sir.
So your copper 2 plus ions, because they're very unreactive, they try to gain those electrons. And they have a very strong tendency to actually gain those electrons. So there's going to be a positive charge that would be building up on the metallic rod. The metallic rod, all these delocalized electrons would be getting lost. I mean, copper ions would be gaining them. So there would be an electron deficiency over here in the metallic rod. But the positive charge cannot build up, it cannot be built up for indefinitely. Eventually, there would come a point that the rod would become so positively charged that it would want its electrons back. I mean, the positive charge would be so strong that it's going to pick the copper atom and pull electrons away from it. So the positive charge can only build up to a certain extent. And eventually, the reverse process would kick in. The positive charge would be so strong that it's going to take a copper atom and pull those electrons back from it, away from it. And at that point, a reverse reaction would kick in and an equilibrium would be established. But once that equilibrium establishes, the charge becomes constant.
Sir, why is the positive charge building? I mean, those copper ions, they are attaching to the rod, but they're eventually turning into copper, which has a zero charge. So why is there a positive charge?
The first thing is copper ions are positively charged. So if anything, like let's assume that they're getting attached, right? So this is neutral. This was neutral copper, right? So if there's an electron deficient species getting attached to it, the whole thing would become positive, right? Do you get this?
Oh, okay.
Plus, the other thing is that they're trying to gain electrons from the metallic rod. So, so the metallic rod over here would obviously become electron deficient. And so anyways, the point is that the positive charge is not going to build up indefinitely. Immediately, a reversible reaction would set in, and then both things would start happening. It would be trying to gain electrons, but at the same time, the positive charge would be so high that the electrons would be pulled back again. And a positive charge builds up on this, and you can measure that positive charge on the voltmeter. Is this clear?
Yes, sir.
Do you, Mohammed, is this clear?
Yeah.
So you've got two types of electrodes. There would be substances that like to gain electrons, and if they like to gain electrons, the charge that would build up would be positive. There would be positive charge built up on the rod, and there would be other types of substances which would like to really lose electrons. So there would be negative charge building up on the rod, and the potential would be negative. So the main or the summary of the chapter is, I mean, this is the summary of the chapter. That is that if the potential that builds up is higher potential, and we're going to higher electrode potential, which, remember, I'm not going to be discussing positive and negative. In terms of positive and negative, I'll be talking about higher potential and lower potential. Higher potential is the positive one. So if the potential is higher, that means the substance really likes to gain electrons. It's got a strong tendency to gain electrons, likes to. And if the potential is lower, if it's a negative potential, then what that would indicate is that the substance kind of really likes to lose electrons. So from now on, I mean, this is the summary of the whole chapter. Like, I mean, you wanted to figure out who wants to gain electron, who wants to lose electrons. So the potentials of all these substances are already calculated. Different electrodes are created, and you can find the potential of each of the substances. And every time, if the potential is high, don't think of potentials in terms of positive or negative, because I told you that that it's the potential difference that matters. For example, if I have a resistor, potential at a point is completely meaningless. So if I have a resistor and there's 0 volts over here, there's 100 volts over here. Can anyone tell me what's the potential difference on the resistor?
100 volts.
100 volts. And if I have 900 volts over here, and I've got 1000 volts over here, what's the potential difference on the resistor?
100 again.
Okay, so it's 100 again. So remember, the value of the potential is a very meaningless value. It's always potential difference. Like it's the same as you're trying to measure the heights of heights of different buildings, right? So let's say there are 3 buildings, and you're trying to measure the heights of the buildings, right? Which one is taller? Which one is so there's always a reference point, and you can keep you can measure the height of the building from the base, right? You're going to get different values, right? I mean, let's say one of them is let's say this is 100 meters. This one is 180 meters, and this one is 40 meters, right? But if I change my reference point, if I try to measure the heights of the building from sea level, so sea level is somewhere over here, then all 3 building heights would be different, right? But the relative heights would still be the same. Like which one is taller, which one is smaller. It doesn't change. It's so the same as with potential. It's potential when you calculate potentials, whether it's negative, whether it's more positive, right? This is what we are trying to measure when we try to calculate voltages. That how positive it is and how negative it is. So it's always a comparison. Like compared to what? Like if I say that the voltmeter is showing a positive value, right? For example, over here, the voltage is coming out to be positive. So the voltage is coming out to be positive compared to what? I mean, what is this thing? I mean, that's in physics, that's known as a ground, right? That's known as that's known as a zero potential or reference point, right? Do you get the point?
Yes, sir.
The same is true over here. Like if I try to calculate the voltmeter and the voltmeter gives me a negative value and it tells me that the potential of this rod is negative, but compared to what? I mean, what is this thing? So the same is over here. Everything, when you try to measure heights, when you try to measure potentials, you always choose a reference point. Like, what's your reference point? Even with masses, you do the same thing. Like atoms, their masses are measured, but in reference to something. Like and they're all measured in reference to carbon 12, right? So you're trying to measure the heights of the building, you always choose a reference point. You change the reference point, you get different values, but that doesn't really matter. I change the voltages, but it doesn't really matter. The resistor still has 100 volts on it. So remember, the value of the voltage is kind of irrelevant. It doesn't really matter. What really matters is the potential difference. So the other thing that I'm going to try and point to you is, what is this thing? This is my reference point. Okay, so that's my reference point. I mean, you make it as a ground, but I mean, there's no ground. Have you ever seen wires going into the ground? I mean, there is usually no ground. It's just a reference point, and the reference point is assigned 0 volts. But the reference point has to be something. It's not. I mean, it's not just like. I mean, it's not just empty space. It has to be something. So this electrode over here has to be positive compared to something, right? Similarly, this electrode over here is negative, but compared to what? So this thing over here is a specific electrode. You have thousands of electrodes. I mean, you can think of an element, you can think of a compound, and you can come up with an electrode. So out of all these thousands of electrodes, you pick one electrode and you measure the potential difference compared to that particular electrode. So the value over here would be negative compared to that electrode. The value over here would be positive compared to that electrode. That's your reference point. And that is your standard hydrogen electrode. So when I wrote the definition, I did write this that the standard electrode potential is the potential difference that is calculated between a standard electrode, like any electrode that you make, but compared to a standard hydrogen electrode, which is your reference point. So this over here is your reference point. I mean, you can change the reference point, doesn't really matter. It wouldn't, I mean, the higher potential would still be the higher potential, just like heights. You can measure the height of the buildings from anywhere, but the taller building would always be the taller building. So this is your reference point. All potentials are measured compared to this. Is this idea clear?
Yes, sir.
Is this clear to everyone? Zaib, is this clear?
Yes, sir.
Yes, sir.
Now, I'm going to come to that later on. Just remember that this thing over here is a particular, out of all the thousands of electrodes, you choose one of them, just like you're measuring the masses of atoms, right? Out of all the atoms, you just pick carbon 12. You compare the masses with carbon 12. You could have picked any other atom, but the relative masses would still come out to be the same. Sodium would still be heavier than hydrogen, and it would still be 23 times heavier than hydrogen. Uh, that fact wouldn't change even if you change the reference point. The same is over here. You can change the reference point, but the standard hydrogen electrode is used as a reference point always. So this is the summary, that you have higher electrode potential. That means it likes to gain electrons, and you've got lower electrode potential. That means it likes to lose electrons. And remember, I told you that positive and negative, that really uh, I mean, you just have to think of it in terms of higher and lower. Like if I was measuring the heights of the buildings, and I increase my reference point to over here, then all the building heights are in negative now. Uh, but the taller one is still the taller one. The smaller one is still the smaller one. So the reference point, you change the reference point, the positive would become negative, but it doesn't really matter. It's still, so always think of it in terms of higher and lower potential. Now the other thing is, yes.
Sir, I have a question. Where you said that once an equilibrium is reached, now, here we attach a voltmeter and try to figure out whether the E naught is negative or positive. So when let's assume that equilibrium is reached. So does that mean that the rod is neutral at that point?
If equilibrium is reached, then a charge that has been built up over here would become constant. I mean, a charge will build up over here. Like it depends initially what happened. If initially, I mean, look at the sodium electrode. Like if initially sodium wanted to lose electrons, there would be a lot of electrons accumulating over here, right? And then the reverse reaction would kick in. But once the reverse reaction has kicked in, now the electrons would become constant, but there's still more, right? I mean, the rod would still be negatively charged. Do you get the point?
So when equilibrium is reached, does the rod actually is negative or is it positive or is it neutral?
It's negative. I mean, what was happening in the start? That sodium was losing electrons, right? Constantly losing electrons, right?
Mhm.
So there was negative charge building up on this rod, right? And when enough negative charge was built up, then the reverse reaction happened, right? But when the reverse reaction happened, the forward is still going on. So the number of electrons would become constant. No one is removing the electrons. Do you get the point?
Yes, but
It
where
just
does the number of electrons becomes constant? कहाँ पे?
equilibrium pe. Because initially it's constantly losing electrons, but once the negative charge is very large, the electrons, they start attracting the sodium ions back again. So now every time a sodium loses electrons, there's a reverse reaction also happening. So what's happening is that the electrons are now becoming constant. I mean, they're not changing.
हाँ ठीक है.
ठीक है? No
Yeah.
one is removing those electrons. Like the electrons would be removed if only the backward reaction is happening. ठीक है? Ibrar, is this clear?
Yes, sir.
So the point is, now the electrons are not going anywhere. The electrons have built up, and now it's always going to be negative. And the same is over here. That initially copper 2 plus wanted to gain electrons, so it started gaining electrons. The rod became more and more positive, and then the reverse reaction kicked in. But once the reverse reaction kicks in, the positive charge is not going anywhere now. It's becoming constant now. The only thing is that the positive charge is no longer increasing. At the start, it was increasing, but now it's becoming constant. So anyways, this one. So remember this potentials. So the basic idea is simply higher potential likes to gain electrons, lower potential likes to lose electrons. So what you're going to do is, like, if you have a data booklet and all the potential values are already given, all these electrode values are already given to you. So that's the whole summary of the whole chapter. Higher potential, just remember, higher potential gains electrons, lower potential loses electrons. So for example, if I were to react silver with aluminium, who's the higher potential? It's silver over here, right? So silver would be the one that would be gaining electrons, and aluminium would be the one that would be, in relative terms, would be the one that would be losing electrons. Is this point clear?
Yes.
Yes, sir.
So
Yes, sir.
so now the thing is very easy, that, like, and remember, it's going to be a comparison. For example, if I want to react cobalt, I mean this, let's pick anyone. Let's say I want to react cobalt with this copper plus one, right? So cobalt is 1.82. So that means that's a very high potential. That means it likes to really gain electrons. Copper, on the other hand, it's a relatively low potential. It likes to lose. Anyone who's, so in the comparison, 1.82 versus 0.52, 1.82 would be the higher potential and 0.52 would be the lower potential. Higher potential gains electrons, lower potential would be losing electrons. So it's always going to be a competition. Like you'll be adding two substances, as I've shown over here at the start. It's always going to be a comparison. Like, I wanted to know what would be the reaction between Fe3 plus and copper 1 plus, right? So the one who's the higher potential would be the one that would be gaining electrons, and the one who's the lower potential would be the one that would be losing electrons. So it's always going to be a relative comparison. So who loses electrons? Who gains electrons? We found our answer. We found how to actually figure that out. You just look at the potential. Who loses electrons? Lower potential. Who gains electrons? It's going to be the higher potential one has a higher tendency to actually gain electrons. Is this clear?
Yes, sir.
Yes.
Achha, so that's the whole chapter. But obviously, I mean, there's a lot of detail to it. So we're going to now focus on the detail. That's the whole concept. Higher potential gains electrons, lower potential loses electrons. So the first thing is, we're going to talk about, so now we're going to talk about in detail, like all the minor details. We're going to figure this out. The concept is clear. So the first thing is, there would be a lot of drawings. So you have to be good with drawings. I mean, not really good, but at least there would be a lot of labeling of drawings. So the first thing is, there are different types of electrodes. So let's quickly cover those types of electrodes. We did the first one. The first one is metal and aqueous metal ion electrodes. That's the first type of electrodes. You might be asked to draw this. So they'll just give you an equation. Let's say they gave you a metal equation like copper. I mean, we just drew that electrode. So they gave you an equation that copper 2 plus 2 electrons in equilibrium with what? With copper. And they're asking you to draw the electrode. This one in the data booklet is it's 0.34 volts. So they're just asking you to draw the electrode. So in a metal and aqueous metal ion electrode, always remember the metal is the electrode. So the metallic rod would be made out of copper. That would be the electrode. And the solution would contain copper 2 plus aqueous ions. And you're just going to connect it with a voltmeter and with a reference point or a reference electrode, which is your standard hydrogen electrode, which I haven't talked about yet. So that's the first type of electrodes. These are the ones that we drew. Is this clear?
Yes.
Okay, so over here you have a lot of metal. I mean, this one, silver and silver ions, same concept. Aluminium, aluminium ions, barium. Uh, so metal with aqueous. I mean, you've got chromium and chromium 3 plus, chromium with chromium 2 plus. So these are all the electrodes that are metal and aqueous metal ion electrodes. But then you obviously have other electrodes that don't have a metal. If you don't have a metal, then there is no electrode. I mean, you need an electrode. You need an electrode. You need a place where, I mean, you need a delocalized electron cloud. You want charge to build up, or you want it to become electron deficient. Only then would, I mean, you need a source of electrons. Like if somebody wants to gain electrons, it can take it from the electrode. If somebody wants to give it electrons, it can give those electrons to it. So if there is no metal, then you have to introduce an electrode, an inert electrode, and that inert electrode is a platinum electrode. So that's going to be our second. So I'll just quickly do the second type of electrode, which is just a second. So let's talk about the second type of electrode, and that's a gas. If I have a gas and I've got aqueous ions. But okay, let's do the second type is, sorry, aqueous ions and aqueous ions. Let's do the gas one later. So if I have aqueous ions only, so how do I set up an electrode? Like, for example, I want to figure out what would happen. Like if I have Fe3 plus in equilibrium with Fe2 plus, the potential is given in the data booklet. It's 0.77 volts. But how did we calculate this potential? Like I've got Fe3 plus and Fe2 plus. I want to figure out whether Fe3 plus likes to gain electrons. If it likes to gain electrons, it's going to be positive, which it is in this case. Vice versa, if Fe2 plus wants to lose electrons, there would be a lot of electrons on the electrode, and the potential would be negative in that case. But since it's a positive potential, that means it's very likely that the reaction would move forward. So how do I make this electrode? Because there is no metal involved. I mean, you've got metal ions in aqueous state. So what you're going to do is you're going to take a beaker and add both of the ions in that beaker. So you add both ions in that beaker. There's Fe3 plus and there's Fe2 plus. So if Fe3 plus wants to gain electrons, right, and wants to become Fe2 plus, where would it find those electrons? So for that, you would need to add or put an electrode inside it. So that electrode is going to be made out of platinum. Platinum is your go-to material for making electrodes. So it has this delocalized electron cloud. So if Fe3 plus starts to gain electrons, it would be gaining those electrons from platinum. And what charge would build up on platinum? It's going to be positive, right? Because Fe3 plus would be taking away electrons from it. Vice versa, if it was the other way around, if Fe2 plus wanted to lose electrons to form Fe3 plus, then all the electrons would be lost on the platinum electrode, and the platinum electrode would become negatively charged, and eventually an equilibrium would be established. So which is why you're going to put a platinum electrode, and you're going to do the same thing. You take a voltmeter and you connect it with your reference point and you measure the voltage. So is this clear?
So I have one question about it. When Fe3 is basically gaining electrons, how do we know if Fe3 is gaining electrons or Fe2 plus is gaining electrons?
Actually, the thing is, I'll tell you. The thing is, because you've added so many Fe3 plus and Fe2 plus ions, right? That eventually, I mean, there could be lots of possibilities. Like Fe2 plus could gain electrons as well, right? But because the maximum number of ions would be in the solution of Fe3 plus and Fe2 plus, like let's assume that you have a billion ions of Fe3 plus Fe2 plus. So at the end of the day, because you have so many ions, the end equilibrium or the dominant equilibrium would be between the two. Do you get my point?
जी
ठीक है? I mean, there would be like Fe2 plus could gain 2 electrons to form Fe as well, right? I mean, that's a possibility as well. But that would not be the dominant equilibrium because you have so many Fe3 plus and Fe2 plus ions in the solution that these minor reactions would be happening, but they're not going to dominate the whole reaction. Is that clear?
नहीं सर मतलब कि if Fe3 over here, how do we know कि Fe3 is supposed to gain electrons from the rod? Why not Fe2?
It can gain electrons, and it can form Fe. But the thing is that the amount of Fe that can possibly form, there would be very few. But the dominant equilibrium would be between these two because they're more in number.
अच्छा तो
But
हम्म,
I mean, you've got 1 billion, let's say Fe3 plus ions. You've got 1 billion Fe2 plus ions. You've added them in the solution, right? So
जी
so the dominant reaction, like if there's 1 billion reactions happening, then 99% of them would be between the two. Like they would be gaining and losing electrons, right? And there would be very
हाँ
minor side reactions that would be happening as well. But so you can kind of ignore them.
got it
Acha, so remember this when you have aqua signs only. So you just put the aqua signs in the solution and you put a platinum electrode in it, and whatever charge that builds up would tell you if it's very positive, that means it likes to really gain electrons, and the equilibrium wants to gain electrons. And if it's negative, that means the equilibrium is kind of favoring the backward side and it's trying to lose electrons. Is this clear?
yes sir
So let's continue next time then, okay? But remember the main concept. Do you have anyone has a question on this?
no sir
So okay, let's continue with this next time.
छोटी सी बात है
Okay, take care.
Allah Hafiz.
Hafiz.